So welcome everyone to another FLAN seminar. Today we'll hear it from Bingbin Liu, a fourth-year PhD student at the Machine Learning Department at CMU. Among other things, she works on theoretical understanding of self-supervised and unsupervised learning, often motivated by findings in vision and language. And this summer, she worked at the Microsoft Research Lab in New York City and worked on transformers for algorithmic reasoning tasks defined with finite state automata. And today's work will be related to this, namely transformers learn shortcuts to automata. Bingbin, thank you for presenting today, and I'm very excited to hear about your work. And so everyone, please welcome her, and you can take it from here.
Well, thank you very much, Lana, for the introduction. It's very great to meet everyone. I'm by no means an expert on formal languages, so I'm really happy to share our work and then get your suggestions and criticisms. Cool. As Lana just mentioned, our work is about transformers learn shortcut to automata, and this is a joint work with my amazing mentors at Microsoft NYC, Jordan, Serbi, Akshay, and Cyril. So the motivation for our work is that we're trying to understand algorithmic reasoning for transformers. We want to understand the reasoning capabilities and internal mechanisms of the network. So some application you might have seen is that this reasoning can be used to solve math or to do code completion. But they're also by no means perfect. And there are tricks such as scratchpad or chain of thought to help improve these models. And so, for example, if we zoom into the coin flip example for chain of thought, then this task essentially is the task for parity. Here we have two inputs, 0 or 1, and there are two states, also 0 or 1, where 0 corresponds to, say, an even number of ones, and 1 corresponds to an odd number of ones. And the dynamic for this task can be modeled by a two-state state machine. Here we have even or odd, and if we see input 0, then we stay where we are, and if we see 1, then we switch the state. More generally, this is a discrete time dynamical system. We call this A, and A is defined by three things: the state space Q, the set of inputs sigma, and also the transition function delta. Here, the transition function will take in the previous state Qt minus 1 and the current input sigma t, and give you a new state Qt. We call this system a semi-automata. So one example we saw is a parity counter. Another example could be a 1-bit memory unit, where we still have two states, but now we have three inputs. If we see the input club, then we set to the state club, or if we see diamond, then we set to diamond. If we see a no op, then we don't do anything. The reason that we call this a memory unit is that we can think of this as, so if we see a club or a diamond, then we're trying to write to the memory. But then if we see a no op, then we read from the memory and don't change the content. Another example that we will see is a 1D grid world, where we have a bounded room in some sense, and then we are moving along the positions in the room. If we see right, then we go right. If we see left, we go left. Unless we're at some boundary, in which case we stay where we are. We can compose these automata into 2D as well, or build much more complicated objects. Also note that there's also automata. So the difference between semi-automata and automaton is that automata have also an accept function phi. But in this work, we only care about the underlying dynamics and not the accepting state. So we ignore the phi and we only care about semi-automata. So in the following, I will be saying semi-automata and automata interchangeably, but in either case, I mean the underlying dynamic. The task for us is that we're trying to simulate the automata. And by simulate, I mean we're trying to learn a sequence-to-sequence function for some sequence of length t. The input of this case will be a sequence of tokens, all coming from the alphabet sigma, and the output will be the state that the process is in at each time. For example, for parity, the input could be 0, 1, 1, 0, 1, and the output could be 0, 1, 0, 0, 1. The first question we might ask is, are transformers even able to learn automata? Intuitively, there seems to be some mismatch because automata has a recurrent dynamics, but transformer, they are non-recurrent. They are parallel and shallow. And just like a quick reminder of transformer, a key component for transformer is self-attention. And in this work, we care about causal self-attention, which means at each position, we can only see all the tokens before the current position. And this self-attention will give us some weight, alpha. Alpha is proportional to the inner product of a key value and a query value. Then given this attention weight, we will, each layer of a transformer will compute the state by averaging all the previous tokens. For example, here's one illustration where we're trying to compute the attention weight for X4. Then we take all the score with X4 and other tokens, and we normalize it and take the weighted average. So back to the question, can transformer learn automata? From the title of the talk, you may have already known that the answer is yes. Transformers are able to learn automata, and they do this via shortcuts, which are solutions with sublinear in T number of sequential steps or rounds. And by sequential steps and rounds, we mean the length of the longest path in a computation graph. For example, for RNN, this will correspond to the sequence length. But for transformers, because they are parallel, this corresponds to the number of transformer layers. It could be independent of the sequence length. As a concrete example, let's again consider parity. There are two ways to solve parity. One way is to do this iteratively, where each qt is the XOR of the previous state qt minus 1 and the current input sigma t. This will correspond to a computation graph like this, where we see that the longest path will be the horizontal one. Another way to do this is via shortcut solutions, and this is a parallel solution, where we say that Q of t is equal to the sum of all the previous tokens mod 2. And this corresponds to a computation graph like this, where the longest path is only length 2. And why do we care about shortcuts? One good thing is that there is a computational advantage. So the computation, the time will be O1 versus OT. And also it's an interesting mode of computation because it's unique to transformers and is not capable by RNNs. So having defined shortcuts, here is the main claim of the paper. We show that shallow transformers can simulate automata via shortcuts, and we show that both theoretically and also empirically. Theoretically, we show that for any length t, transformer can solve it with sublinear in t number of layers. The most general result will be a log t layer simulation, and this applies for all automata. It's also a lower bound for the most general case. If we consider only a subset of the automata, which we call solvable automata, then we can remove the dependency on t, and the number of layers required will only be depending on the size of the state. For both these cases, these are refinement of classic ideas in Barrington theory. Then in an even more special case, we consider the one-degree world, that we just saw. And in this case, we have O1 layer simulation. Then empirically, we first show a positive result that in practice, training shallow transformers with SGD can indeed find shortcuts. However, there's also a downside. So these shortcuts, they are not as robust as RNNs when generalizing OOD. We can try to fix this brittleness by trying to turn the transformer into a recurrent solution via via scratchpad training. The good thing is that now we can do well OOD, but the downside is that we lose the ability of being parallel. So that's the outline of the talk. Is there any questions? Okay, so please stop me whenever everything is unclear. Cool. So let's start with the theory part. The first question we ask is, do transformers always exist? Recall that our task is that for each time t, we are trying to compute the current state qt. And the qt is a transformation from q0 given all the transformations that's induced by the input sigma 1 to sigma t. And each sigma specifies a function that is a state-to-state function, which is the partial application of the transition function given the input sigma. So essentially, the block of transformation in the box is a composition of functions. Again, as parity, to use parity as a concrete example, here for input 0, the the corresponding state-to-state function will be this delta 0, and that's the identity. For input 1, then we have a swap function. So in this sense, the function composition is equivalent to matrix multiplication. And the hint in this case is that we have a O log T layer solution. And the keywords for this is divide and counter. So basically, we're trying to build a binary tree where at each node of the tree, we're trying to compose two functions together. And since we're composing over T items, the overall depth of the tree will be bounded by log T. And this can be done in parallel as well, so we can do the entire thing for all capital T of the positions in time log T. Okay, so that's the first solution. Then the next question we have is, can we do better than log T layers? We already saw one example.
Bingbin, can I interview just for a second? Can you say what you mean exactly by a shortcut?
Oh, yes. Okay, I should clarify better. So by shortcuts, we don't mean the shortcut that we typically see in the literature, where we're saying the shortcut is something that's only fitting the training distribution, but not generalizing OD. By shortcuts, we only mean the definition that we saw here. So in terms of the computation depth, the length of the longest path in the computation graph will be sublinear in T.
Okay.
So for example, yeah, so for example here, we call the right thing as a shortcut, since here the longest path is of length 2.
Okay.
But the thing on the left is not a shortcut, since it's like it has T steps.
So it's just a sublinear solution.
Yes, yes. And shortcuts, technically, they can generalize to all the distribution shifts as well.
Right. Okay, great. Thank you.
Yeah, thank you for clarifying. All right, so back to our brain teaser. So can we do better than log T layers? We already saw one positive answer for this, and that is the parity. For parity, as we just reviewed, it only required 2 layers. And the idea for this is that we only need to count the number of ones in the current inputs and then take mod 2. And in generally, counting will suffice if the function composition is also commutative. So by definition, function composition is associative, but if we additionally have commutativity, then counting will suffice. But then the question is, can we find some solution with sublinear, with less than log T layers? Any ideas? Well, the answer is still yes. And to see this, let's go through one example. The example we consider is a reversible car driving on a circular road. So in this case, we have 2 inputs, D for drive, where we drive one position forward, and U for U-turn, where we turn around. And there are 8 states correspond to 2 directions times 4 positions. And the task is going to be, so given the input DDDU, DDUUD, can we try to determine all the direction and position starting from the initial state of clockwise and 0? And if you want to solve this, then the first observation you might have is that in order to determine the direction, it suffices to solve a parity task on U. More concretely, so here, starting from U being +1, if we see D, then we don't change U. But then if we see U, then we flip the parity bit. And if we see U again, we flip it again. So in the end, we have the parity bit is -1. So the direction is counterclockwise. And then if we know the direction already, another thing we may note is that the position will now be the position can now be computed as the sum of the sign counts mod 4, where the sign is given by the parity of U. So here, for example, we have 1, 1, 1, and then for U we're not moving, so it's 0. And then because here the parity bit is -1, so for these 2 D, we count as -1, -1. And similarly here, we count as -1. And then overall, the sum is 0. 0 mod 4 is 0, so we have 0. So the idea here is that we're decomposing this this problem into two parts, where the first part will also affect the second part. This idea can be generalized to automata. And to see how we can do this, we first need to define something called a transformation semigroup. Recall earlier that we say our task is essentially trying to determine Qt, given Q0 and all the transformation induced by the inputs. Each input corresponds to a function sigma, delta L sigma. And the transformation semigroup for some automata A is this T of A, that is the set of all the functions given by these delta sigmas and also their function compositions. For example, for parity counter, it corresponds to a cyclic group C2. We can also generalize this more to, for example, C5. And just a quick reminder on groups. The group G is a set with a binary operator also on the G, which has a set of 3 properties. The first is that the binary operator should be associated. And the second property is that the set should contain some identity element. And the third thing is that for each element in the set, it should also have an inverse. But in this following example, we can see that the group axioms are not satisfied. So here, for example, if we go back to the memory unit, then the corresponding structure is not going to be invertible. For example, for the first row here, regardless of the previous thing we're composing of, after composing with diamond, we always get diamond. So in this case, we don't have a group anymore. And the structure we have is a semigroup, which is a generalization of group that only need to satisfy associativity. Usually, we also include an identity element as well. In this case, a semigroup can also be called a monoid. So the takeaway from this slide is that there's a natural correspondence between a semi-automata A and its corresponding transformation semigroup T of A. And then in the following, we'll be decomposing this T of A to see how to decompose the semi-automata. So going back to the example, so the result we'll be using is Krohn-Rhodes, which says that all semi-automata can be decomposed into mod and resets, these 2 operators. And by decomposition, let's first start with groups. So similar to prime factorization, a group can also be decomposed into some prime factors in some sense. So the classic result by Jordan and Hodder said that any group G can be decomposed into a series of groups Hn to Hi, where for each element in the series, it is a proper normal group of the previous element in the series. Also, each of the quotient group between the adjacent elements are simple groups. And these simple groups can be considered as prime factors. And by solvable, we mean that each of the quotient group is additionally abelian. So the decomposition of group is given by Jordan and Hodder already. But then for semigroups, in this case, we only have associativity. So it's a much more complex case. And this case is solved by Krohn-Rhodes. To see the intuition about why it's more complex, the main reason is that there's rank collapse. So one analog for this is that for group, you can consider as a group operation as n players are sitting in n chairs, and then the group operations are only permuting the chairs. So in this case, the size of the permutation group, the transformation semigroup, can be n factorial. However, for semigroups, we can in this case, the analogy could be n player in musical sofas, where the operation could permute the players and also put 2 players in the same sofa. And that's the merge operator, for example. And then once they are in the same sofa, these players, they will move together in the future movement as well. So in this case, the size of the transformation semigroup will be much larger. So now we see that there's the problem of the rank collapse. So in order to track all the rank collapses, we need something that can track all the history. So essentially what we have is a tree like this, where at each of the nodes in the tree, we only have rank collapsing group transformations, but among the nodes in the tree, we can collapse the rank. And because there are at most size of Q rank to collapse, the depth of the tree will be at most size of Q. If we're trying to map it back to transformer layers, then the first thing we have from Jordan Holder is that for all solvable groups, we can solve this by log in a group size number of layers. And the only element we need for this is to be able to implement the mod counter and the parity counter. If we want to further handle semigroups, then we need something called a permutation reset subautomata, where permutation corresponds to the group operations and reset corresponds to the rank collapse. For this case, it's going to be upper bounded. As we saw earlier, the size of the group is much larger. So in this case, it's going to be upper bounded by something that's the size of the state space, and also the time a log factor. So this is saying that each of the node in the tree is upper bounded by this number of layers. And then overall, because there can be at most size of Q levels of the nodes, so the overall complexity we have will be Q squared. All right, so going back to the transformer implementation, since we know that we only need to model the mod counter and the reset operator, so it suffices for us to model these two basic units. For mod, it corresponds to, say, the parity counter, and this could be implemented by the uniform type of attention. Then for the memory unit that corresponds to reset, we can do this via sparse attention. Also, we want to clarify that we do not claim that transformer they actually learn this in practice, but still it's an interesting way to see that theoretically it's capable of doing this. And a really interesting future work is to see, can we probe the transformer to understand what is the solution they're learning? All right, so that's the second solution. And then the more ambitious goal to see is that, so can we solve this in O1 layers, where O1 is even independent of the size of the state space? Again, we already have one positive answer, and that's the parity case. In parity, we can do this in 2 layers. But in that case, we already saw that parity is a commutative group. But for this case, if we only have non-commutative operations, then can we still find some special case where we can solve this? The example we see here is the one-D grid world, where we have 2 operations, L or either going to left or right, and the state is the location in this bounded room. So we can go to either left or right, up to the boundary effect. So for example, on the right, if we're starting with state 0, and we see a left, then we cannot go further left, so we stay where we are. And then we go right, left, and then we keep going until we see all the right, until we reach the right, we reach the rightmost boundary, then we stay where we are, and then we go back when we see left. So one intuition when you're trying to solve this is that, so due to this boundary effect, it might be the case that we have to know our previous state in order to figure out where we are currently. And this intuition turned out to be wrong. So then the brain teaser here is, can we design some parallel algorithm that can still compute this, this function from all the sigmas to the states q's? Now think about this for a bit. So the key answer here is that we need some parallel boundary detector. And the reason that a boundary detector is good is that if you already know the last position you're at some boundary, then in order to figure out where you are currently, you can discard all the history before that last boundary and only focus on the part that's afterwards. However, the part that's after the last boundary is very easy, because in that part, you only need to do a prefix sum. That, as we saw in the parity case, the prefix sum is solvable in only 1 layer. So the key thing here is to figure out how to do the parallel boundary detection. And in fact, a transformer figured this out earlier than us. The solution it gave us is that the first layer is some uniform attention. Then in the final layer, some of the head will implement the boundary detector for the leftmost position. So here, for example, these attention bars correspond to the positions. Oh, sorry. The yellow attention bars are the one that's given by the transformer, and the dots are the ground truth. So here we can see that the attention bars align perfectly with the true positions. So the plot in the middle is a boundary detector for the left boundary. And similarly, we also have a boundary detector for the rightmost boundary.
Sorry, can you explain where these plots are coming from? Or is this a transformer you trained, or yeah, sorry.
Oh, sorry, yes. So it's a transformer that we train on this Krohn-Rhodes task.
I see. Okay.
So yeah, so we saw for the first plot is the attention map for the first layer. And for the middle and right plot, these are some of the head from the last layer. Not all heads are as clean, but there are some clean heads which give you these patterns. Cool. So now we know that our goal is to detect the boundary. We can see how can we solve this. So the idea for the boundary detector is that we first try to compute the prefix sum, and this is the normal prefix sum. We don't consider a boundary in this case, and so we call this sum values at z of t. Then once we get all these zt's, in order to find a boundary, we first find some t unique, such that starting from t unique to the current t, the set of z values have s+1 unique values. So recall that S is the last state. So S+1 corresponds to the size of the state space. And then once we found this T unique, we claim that the last time that the process is some boundary is the later position between the max and mean position in this window. So for example, in this one case, we see that the T position is the last position, and the T unique is going to be this position, since in this case we have four unique values. And then this T final is going to be the max between this position and this position. So we're saying the max is the T final here. And indeed, that's the last position where we're at some boundary. We have another case where we do not traverse all the states, but we stay at one of the walls for more than one step. In this case, we can verify that this algorithm still gives you the correct boundary. Okay, so that's the intuition for this algorithm. And that's all the theory part. So just to recap, for the theory part, we have three cases. The first case is the most general case where we can solve all some automata with log t number of layers. And the keyword here is that we're trying to do parallel prefix sum computation. This is also the lower bound for the most general case. In the second case, we saw that for solvable automata, we can solve this with polynomial in the state space number of layers, but that is independent of t. And the keyword here is that we're trying to do factorization via Krohn-Rhodes. Then in the final case, we saw that for some special example, we can do this in O1 number of layers. All right, any questions so far? All right, cool. So now we can move on to the experiments. So recall that our task is trying to find this map between all the input sequence and the output sequence. The zeroth order question we ask is, are shadow transformer able to represent this? And from the theory part, we say that the answer is yes. Then empirically, we want to solve the following questions. The first question is, in practice, can SGD trained on transformers find these shortcuts? To this, our answer is yes. And then if we can find the shortcuts, are there any limitations for them? Oh, sorry. So Q2 is saying if we are training the transformers with some limited supervision, can we still do it? And the answer is yes, to some points. Then the third question will be, if we're finding some shortcuts, are they still robust if we're changing to unseen inputs, so like OOD tests? For this one, the answer is no. Especially compared to RNNs, transformers are much less robust. Then the next question we ask is, if we know that they're not robust, can we guide transformers to still learn the recurrent solution which are robust? And the answer is still yes. Then finally, an open question that we hope to answer, but we don't have the answer to, is how do we design some architecture to solve reasoning tasks? Okay, for the last answer, we don't have. For the last question, we don't have an answer, but for the first 4 questions, we can dive deeper for that. Oh, please.
Oh, what do you mean by limited supervision? In the last slide.
Oh yes, sorry. Yeah, for supervision, so we mean that we can either supervise on the on some function of the state space rather than the entire state, or we're given the supervision not at each position of time t, but only at some positions.
Oh, okay.
We'll see them later. Yeah. Cool, thanks. All right. So these are the 4 questions, and the first question we're trying to answer is, in practice, does SGD find the shortcuts? And then the answer is yes. So the table here is the result for different semi-automata and different transformer depth. So each row here corresponds to one type of semi-automata, and each column corresponds to one depth. So one of the I think the table is pretty dense, so I'll summarize some of the key results we can show. So firstly, the very simple example, the grid row that we saw, they can be very easily solvable. Another example we put here is the Dyke language. Some prior work also showed that Dyke can be solved in 1 layer, in 2 layers. So in O1 layer, basically. And then for a second group, we consider cyclic groups. For these ones, we found that the training is quite unstable. And this the training instability could be a possible reason for the next result unparity in Better-Mishra et al. So but another difference between theirs and ours is that their evaluation is on the entire sequence. So the entire sequence is correct only if every position in the sequence is correct. But in our case, our evaluation is on per position. So it's the so for each time position, we will check if it's correct or not, and then we take the average over all the positions. So the open challenge here is, how can we improve the architecture and also the training pipeline to make this more stable? We also checked some other abelian groups, and for this case, we saw even worse instability. And we found that in general, training with higher depth could help stabilize training. And finally, we saw that for some even harder groups, for example, the dihedral group that we just saw, and also A5, which is non-solvable, and S5, which is NC1 complete. For these groups, transformers can still solve them. They in general would require deeper layers, and also it's going to be some open challenge to see how can we interpret these solutions. All right, so that's the first question for possible results. And then moving on to the limited supervision. So in this case, we try to reduce the amount of state information we have during training. The first case is indirect supervision, in which case we don't train on QT, but we train on some function of Q of T. So for example, for the grid, for the die case, we don't give the entire stack, but we only give the top of the stack. And for grid world, for example, we don't supervise on each position, but we only check on if the position, if the process is on some boundary or not. And for these tasks, we see that in general, the transformer can still do pretty well. However, if we, oh, sorry, please.
So I'm wondering about the evaluation in that table. So are you, when you measure accuracy, are you looking at the same metric, like the indirect output, or are you?
Oh, good question. Yes, it's still the same metric.
Okay, cool. Thanks.
Yeah, so the training and test, they're both sorry. They're both also a function of QT.
I see. Thanks.
Yeah, thanks. Okay, and then the more severe problem we saw is in incomplete supervision, in which case we don't review the state at each position, but for every QT, we only give the label with some probability. So here you can see that if we always review the label, the transformer is doing pretty well. However, as we reduce the probability of revealing the label, then the performance drops. So basically, the transformer stops to learn. But in both cases, R and N can maintain a perfect accuracy. So here is still like one small gap between transformer and RNNs. Another thing we found is that the shortcuts learned by transformers, they contain some solutions that are not robust to OOD. In this case, let's consider parity. We're still in the normal training regime, and we also but we changed the evaluation. In the evaluation, we try to evaluate on something that's different from the training distribution. So recall that for shortcuts, the thing that we guess the transformer is doing is that it will first compute the sum of all the inputs and then take mod 2. In this case, so for training distribution, we're setting each position to be IID, to be equally likely to be 0 or 1. So the sum will be concentrated tightly around T over 2. But for evaluation, we saw that if we change the value of this count drastically, then the model will fail to generalize. One example we saw here is here. So here the x-axis is number of ones. So that's the sum quantity here. And the y-axis is the performance. The light blue line here showed that as we go further to count that is unseen during training, then the performance is much worse. The dark blue line here is the normal training of GPT, where we found something slightly bizarre, is that for lower counts, even though that we have seen them during training, the model is still doing pretty bad. And the reason for this is that it's likely because the model is correlating the counts with the positions. So for training, these lower counts likely occur earlier in the sequence. However, during testing, these counts can appear anywhere in the sequence. And in that case, this correlation is broken, so the performance is poor. And this, if we compare this line with the light blue line, here you can see that if we shift the position during training, where we try to break the correlation between the position and the count, then indeed transformer only fail at higher count that's unseen during training. Another way to verify this is that if we're trying to generalize to longer sequence length, in this case, if we don't bound the number of ones that we see during training, if we don't bound the number of ones that we see in the samples, then as we increase the sequence length, the number of ones gets larger and the performance drops pretty quickly. However, if we bound the number of ones to be only 20, then the performance is not affected by the length by much. So these are two examples to show that indeed the transformer might be learning something like this, and then generalizing the mod 2 function is problematic. Okay, so So we have now seen that there's some issues with transformers. So can we fix it? And the answer is still yes. In this case, the way we try to fix this is to force transformer to learn a recurrent solution. So during training, we train the transformer to output only one step at a time, rather than computing all the states in parallel. And for evaluation, we evaluate at different distributions or different length. So here, we compare different variants of transformers. The key takeaway here is that if we do not, if we only train the vanilla transformer, then it will fail to generalize either to a new distribution or to longer sequence. So here, the dark blue line corresponds to the vanilla GPT. On the left figure here, we're changing the probability of seeing one in the parity task. Here we can see that as we vary the input distribution, the performance drops. And for the middle and the right plot, we're trying to do length generalization for both parity and for Dike. In both cases, we can see that the transformer gets the performance gets much worse as we shift as we increase the sequence length further from the training distribution. In all the three cases, the RN, and that is the right line here, it stayed perfect in all the cases. And the way for us to fix the transformer is that we're trying to add the scratch pad and the recency bias, so that now we get this golden line here. So the golden line here is still perfect in these scenarios. So the takeaway is that if we force the transformer to be recurrent, then we can do well. However, the question that's unclear is, so can we learn some shortcuts that can still generalize? Okay, so the takeaway for
Could you explain what the scratch pad and recency bias is?
Oh, sorry, yes. So for scratchpad, the idea is that we are, so we're training transformer in a recurrent mode. So I have some of the slides to demonstrate what I mean by scratchpad. Right, so this is the vanilla mode for GPT, where things are computed in parallel. We want to do this in a sequential order. So the thing we do is that if we have some y, say this yi, we try to feed it back into the inputs. So we start from say y0, then we compute y1, and then we feed it back into the input, and then compute 2, and then back to 3, and so on and so forth. So essentially, if we can compute the previous input perfectly, then the next input is only so the yn would only depend on this y-1 and the current input. And because of this, we further added the recency bias to force the transformer to only focus on the last inputs. So there are two ways we can do this. One way is to say that we know it has to be this case, so we force the attention to attend to two things only. Another way is to add this recency bias where we don't force this, but we encourage the transformer to focus more on the recent positions. Is this clear?
Yeah, thanks. But that's of course no longer going to be sublinear time, but right?
Oh yes. Oh yeah. So this scratchpad will turn transformer into the recurrent mode. So it's no longer a shortcut, but it can fix the problem of the OOD. So basically, currently we see that transformer is able to do both a shortcut and a recurrent solution. And currently it's unclear. So can we take the best of the both worlds, basically?
So it's not like what you do is you train in some like the scratchpad mode, and then you get rid of the scratchpad mode, let it return, and magically it has now learned one of these shortcut solutions. That's not the case.
No, yeah, right.
Okay, thanks.
But that's the interesting thing. I've never tried to train a transformer in scratchpad and then and then use it in a parallel mode. So
Yeah.
the thing that's most okay. So Scratchpad is proposed by No et al. And in their paper, they take a pre-trained transformer and then they. Oh, sorry. I think Scratchpad training is done during training as well. They have a slight modification of this. So the way they do is that they put all the Scratchpad at the beginning, and then you compute this in the sequence. So for our case, we're kind of interleaving the Scratchpad and the inputs, and also for Scratchpad and also for the later train of thought, the thing they do is that they take a pre-trained transformer. They don't train everything from scratch again. They're kind of using Scratchpad as a way to better use a pre-trained model. And for our case, we're training everything from scratch as well.
Which seems appropriate given that it's a scratch pad. Ha ha ha.
Yeah, right. Scratchpad. Yeah, the naming is pretty proper, I say. All right. Cool. So going back to the takeaway for the experiments part. So first, we saw a positive result that transformer can indeed learn good integer solution, and these are the shortcuts. And we saw from the big table that number of layers required roughly match our intuition about the difficulty of the tasks. And then we also have some understanding about how it's solving this. For example, in the parity case, we have some evidence to show that the transformer are indeed learning a solution that's taking the sum of all the inputs, the mod 2. And in the grid world, we saw that transformer can indeed find a boundary detector. There are still some challenges, and so the most challenges lie in the OOD setting. So transformers themselves are not very robust to OOD unless we turn them into a recurrent solution. So going back to the takeaway from the entire paper, in this paper, we show that transformer can learn shortcuts to automata. And for theory, we show that there are 3 modes. The first mode is the most general case where we can solve this in log T layers. And in the second case, if we constrain ourselves to a subset of solvable automata, then this can be solved in polynomial in the state space number of layers. Then in a very special case, we can even do this in only 1 layer. Empirically, we found that on the positive side, training shallow transformers can indeed find shortcuts. However, they're also brittle OOD. We can turn them into recurrent using a combination of Scratchpad and a recency bias. But the question is, so can we try to make a shortcut solution still generalizable? So for some future directions, one thing we want to do is that we want to better understand and characterize the shortcuts. As we mentioned earlier, the constructions we have for the Krohn-Rhodes, it's not the thing that we claim the transformer is finding in practice. So better understanding what they actually do is a quite interesting problem. Also, we would like to have the best of both worlds. We want to have some shortcuts that can also extrapolate. And for this one, it's unclear, for example, if we try to scale up the model, can some of the drawback disappear? Our current guess is that it's probably not going to solve some of the problems, but there might be some more interesting phenomena coming up. And the end goal here is if we can solve these toy tasks, can we eventually do better on